Hi everybody, it's Cameron here. Today we're going to be starting a new subject, and a new series of videos based on GCSE chemistry. Okay, so we're going to start with atomic structure. This is the first chapter of 15, I believe. It's important when it comes to chemistry to really understand the basics and the first couple chapters. I'm talking about topics 1 to 3, probably up to and including the periodic table, before moving on. Okay, a lot of chemistry is based around, all of chemistry really is based around these few chapters. Okay, so if you don't understand them, it's going to make the entirety of chemistry very difficult for you. So make sure you understand these, do some examples, different types. We're going to try go through all the different variations that we can to clear up as many questions as you may have on the topics. And yeah, let's get started. So the first chapter we're going to be covering is the atomic structure. So the atomic structure includes the atom, the history of the atoms, isotopes, ions, separating mixtures such as using fractional distillation, chromatography, as well as the electronic structure and chemical equations. Okay. A lot, I know, but we're going to get through it, and hopefully it's going to be a lot easier for you, as this is a lot more condensed, I think, than the book chapters. So, to start with, we have to realize that every bit of matter around us, be it gas, be it a solid, be it a liquid, everything is made up of atoms. Okay. Now, the only differences between these atoms, so the only differences between the atoms in the board behind me, the atoms that make up me, the atoms of the gas that I'm breathing out, are the different numbers of protons, electrons, and neutrons. Okay, so everything is made up of atoms. Atoms are all made up of just protons, neutrons, and electrons. Okay, that's the only difference. When it comes to protons, the proton number is going to distinguish the atomic number of a certain element. Okay, now what do we mean by an element? An element is a pure substance. Okay, so we have a periodic table, which we'll get to in later lessons. And that periodic table is a list of all the known elements to man. Okay, so we don't have board on the periodic table or skin. Okay, these are what we call compounds. But a pure material is an element. Okay, and an element is distinguished from other elements by the number of protons it has. Okay, so if you look at pencil lead, okay, hopefully the camera will focus. If you look at pencil lead, okay, the black part of the pencil, we call it the lead. It's actually not made up of lead, although lead is an element. It's made up of carbon. Okay, now that carbon is going to have 6 protons, I believe. Yes, it's 6. Okay, so every carbon atom in this pencil lead is made up of 6 protons. Okay, if somehow we were able to add one more proton to that lead, all the lead atoms in here, to all the carbon atoms in this pencil lead, it would all of a sudden turn into a gas by just adding one proton. That gas would be nitrogen. So the only difference between a nitrogen atom and a carbon atom is one proton. Okay, so we call that the atomic number. It distinguishes elements. Okay, protons are also going to be positively charged. Now, protons are found in something called the nucleus. And as well as protons, we find neutrons in the nucleus. Okay, so neutrons are a neutral charge, and what they're going to change is the mass of the atom. Okay, so how that works exactly is we can't change the number of protons in an atom. Okay, the number of protons stays fixed because we can only work with that element. Okay, atoms can't usually be split up. Okay, doesn't usually happen. but the number of neutrons can change, and we'll get to that later. It's called the isotope. But the mass number of a specific element of an atom is going to be the protons plus the neutrons. Okay. And finally, electrons. So in the nucleus we have our protons and our neutrons, and flying around them are something called electrons. Electrons are negatively charged particles of the atom. Okay, and we say that they are located in the orbit around the atom. So they're flying around the atom. We call it they are orbiting around the atom, like the planets around the sun. Okay, so when two or more different elements are bound together, okay, they're called a compound. Now, when we're talking about bound together, okay, it's like to make skin. It's a couple elements that are going to be bonded together. Same thing with the board behind me, same thing with this wooden cabinet here, okay? And what happens, it's the interaction between these electrons that bonds these elements together to make certain compounds, okay? So it is not protons interacting with each other or nucleuses interacting with each other. It's their outer electrons that are going to be moving around to form these chemical bonds with other elements. Okay, and then depending on the charges of the elements, which we'll get to later, there will be different numbers or different ratios of elements in a compound, such as H2O. Okay, 2 hydrogens for 1 oxygen. But we'll get to that later. Just know that electrons are going to be what causes elements to bond together. So, where did this idea of atoms come from? Because remember, up until quite recently in human history, no one had any idea what everything was made of. There were many theories. Initially, they thought mice came from water and wheat that was left in a jar overnight, and a mouse would appear. Okay. This is obviously just because the mouse was attracted to it and fell into the jar. But without scientific proof, you can't really convince people that everything is made up of these tiny little balls that are spinning around other tiny little balls, you know? So, where did this idea of atoms come from? It was a man called John Dalton that originally devised the closest representation of how we perceive atoms as today. There were before him, okay, but John Dalton's idea that everything was going to be made up of these tiny, small, indivisible particles, okay, and that all the atoms of a certain element are going to be identical to one another. Okay, this was the idea that John Dalton put forth to the scientific community, and it was accepted. Beforehand, they thought that possibly atoms could be protons, neutrons, and electrons all in one ball called the plum pudding model. Okay, but it was John Dalton that had this idea of electrons spinning around a central nucleus, and that you could not divide an atom into anything smaller but an atom. We now know that this is incorrect, and we can divide them into protons, neutrons, as well as quarks, which you will get to probably in high school chemistry or university chemistry. But yeah, John Dalton's model was the closest to the current model in history that we came across. Okay, but Dalton did not account for isotopes or the existence of different forms of the same element, which was a concept that was central for modern atomic model. Okay, so he didn't know about protons and neutrons. He just knew that they were the smallest particles, which was kind of correct. Okay, so let's look now at how an atom of an element can change even if the element itself stays the same. So what are we talking about here? We're talking about an element, so something with a set number of protons. Okay, let's take carbon for example. Carbon has 6 protons. Normally carbon would also have 6 electrons for those 6 protons, so that their charges balance out. 6 positives 6 negatives, 0 charge. Okay. Now, the number of protons cannot change. So the number of positive particles cannot change, but the number of electrons can change. And that's when you get ions. So ions are when atoms gain or lose electrons and become either negatively or positively charged. Okay. So if something gains an electron, it is going to have more electrons, more negative charged particles, than protons. Okay, positively charged particles. So if it gains electrons, it's gaining negativity and it becomes negatively charged. Now, if it wants to be positively charged, it cannot gain protons, but it can lose electrons. It's losing negatively charged particles and therefore will be more positively charged. Okay, so we get a positively charged atom by losing electrons. We get a negatively charged atom by gaining electrons. Okay. So we usually have a sort of net charge, and we're going to get to this when we do the periodic table. Certain elements are going to want a certain number of electrons to become stable. Okay. So oxygen, for instance, has 8 protons. Okay. And this cannot change, but when it is neutral, it's going to have 8 electrons. Okay, if this oxygen bonds with a hydrogen, it's going to gain 2 electrons, H2O. Okay, it's going to gain 2 electrons, and it's going to become O2 minus. Okay, oxygen with a 2 minus charge. And notice that that 2 minus charge we put at the top, not at the bottom. Okay. So it becomes O2 minus, it becomes an oxygen ion, a negatively charged ion. Okay. Now, that was electrons. If your neutrons change, we get what's called an isotope. So if you remember, our neutrons and our protons together are going to give us our mass number. So neutrons plus protons give us our mass number. The number of protons cannot change, but the number of neutrons can. So the number of neutrons is going to affect the mass number. So when we have something like carbon, carbon is going to have 6 protons. Its atomic number is 6. It will not change, okay? But the mass number can change. You see that? And this is because over here it has gained neutrons, okay, to become carbon 13. You see that? Okay, so both of these are carbon atoms, but they are isotopes of carbon because they have differing numbers of neutrons, but the same number of protons. Okay. Okay, so let's look at electron structure. So when it comes to how electrons are going to be spinning around our nucleus, we know that they are going to be spinning in different energy levels. Okay, so they don't just spin in the same orbit, they have different levels that we call shells. Okay, now the lowest energy shell is found closer to the nucleus, and as we get further away from the nucleus, the more energy those electrons have. Okay, so when it comes to level 1, it has a maximum of 2 electrons. After that, level 2, okay, has a maximum of 8 electrons. After that, the next level has a maximum of 8 electrons. After that, don't worry for now. Okay, we're going to get to that, not in this lecture series, but eventually you'll get to the quantum mechanical model of electrons, and that will explain what comes after level 3. Okay, but right now just worry about 2, 8, 8, and then whatever's left over if it gets to that. So I suggest doing some examples of this to just see how it works. But when it comes to something like calcium, calcium is going to have 20 protons, which means that it's going to have 20 electrons initially. Okay, so to have 20 electrons, the electron configuration is going to be 2, okay, because the first energy level is going to be full. After that, the next energy level is going to have 8. So total now we have 10 electrons. We need 10 more. Next level is going to have 8 again, so you can count 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, sorry, 18. Okay. And then we have 2 left over here. But that level is full. So we have to go to the next energy level, to 18, 19, 20. You see that? Okay. So only once an energy level is full can we move to the next energy level and start filling that next energy level. Now, to become more stable, all atoms want to have a full outer level. So that final level of theirs, they want to be full. They want to have the full number of electrons. Okay, so this can be done by either the element giving up its electrons. So in the case of calcium, it's a lot easier to lose 2 electrons than it is to gain 6. But we'll get to this in chapter 3. Okay, but the point is they want a full outer level. It can lose electrons to get the last outer level's full level, okay? Or it can gain electrons to fill its final one. Okay, something like group 8 on the periodic table has 8 electrons in the outer level. These are called noble gases and they are stable. Okay, they don't bond with anything. But something like group 1, they only have 1 electron in the outer level. They are very reactive because they are ready to get rid of that 1 electron so that they can have a full outer ring from the previous ring. Okay. Yeah, so when it comes to chemical reactions, a chemical reaction is basically when we're going to have some elements or compounds, some chemicals, okay? They're going to react with one another. Now, what does it mean to react? To react means that there are going to be chemical bonds that are broken or formed, okay, between compounds or between elements or between compounds and elements, okay, and a new product is made. So a new compound or another element is going to be in a different form, let's say, that wasn't there before, okay. So let's say it was something like copper sulfate in the beginning, and now you're going to have copper. You see, it's going to be different. It's going to be something that has been created that wasn't there initially. That is a chemical reaction. Okay. Now, when we talk about chemical reactions, we're going to be looking at chemical equations. Okay. Let me get my pointer out here. So, when it comes to chemical equations, we're going to have reactants on the left, and they're going to be creating products on the right. Okay. When we talk about these chemical equations, we talk about the law of conservation of mass or the law of conservation of matter. This basically means that matter cannot be made or destroyed. It only changes form. Okay, so whatever you start with, you have to have the same amount of that specific element in the product, in the end, okay, and vice versa. Okay, we're also going to be using these abbreviations, S, L, A, Q, and G, okay, and what they symbolize is what form the compound or the chemical is in. S is for solid, L for liquid, we use that for water only, H2O. AQ is aqueous solution, so that's something in a liquid form, okay, and then G is gas, okay. So when it comes to these chemical equations and the law of conservation of mass, what we're going to have to do is balance these equations sometimes. So how you'll get this is in a test, they'll give you a formula like this. Carbon dioxide plus water gives us glucose, C6H12O6, plus O2, oxygen. Okay, this is photosynthesis. Now, straight off the bat, we can see there are more carbons in our products than there are in our reactants. Okay, So this is an unbalanced equation. So how do we balance this equation? So you start out by listing all your elements in your reactants and then list them in your products. Okay, so copper, hydrogen, and oxygen. It's always important, and I find you don't have to, but in my experience it really helps to do hydrogen and then oxygen last. Okay, those two always seem to be a bit of deal breakers when it comes to balancing these equations. It's better to balance oxygen the very last and hydrogen before that. Okay, and then the rest of your elements before those two. So you're going to list your elements, you're going to count how many you have in your reactants and in your products. Okay, so in your reactants we have 1 carbon initially, we have 2 hydrogens initially, okay, and we have 3 oxygens in our reactants. You see that? So we start out with 3. We do the same thing on this side, 6 carbons, 12 hydrogens, and 8 oxygens initially. Okay, 8 oxygens. So ignore the colors for now. Okay, then what we're going to do is we're going to start adding coefficients to balance out the number of elements. Now, what is a coefficient? A coefficient are these numbers in the beginning of the molecules. Okay, so important, you cannot change the small numbers. Okay, you cannot change those because then we're changing the molecule. Okay, H2O is water. H2O2 is something completely different. That's actually quite poisonous for you. Okay, so you cannot change or add little numbers, you can only add coefficients. These coefficients, however, are going to change both elements. Okay, because it's saying now if you have H2O, you have 2 hydrogens and 1 oxygen. If you have 2 H2O, you're going to have 4 hydrogens and 2 oxygens. Okay, I hope that makes sense. So initially we have 1 carbon in our reactants and we have 6 in our products. So we're going to add a 6 here. Now we have 6 carbons. But once you add your coefficient, you must update it with what it has changed. Okay, so by adding a 6 here, we've changed the number of oxygens. Okay, excuse my computer's fan, it's about to take off, I think. But so we're going to have now a different number of oxygens that we initially had. Okay, so we've got to update that. So now we are going to have 12 oxygens. Okay, 6 multiplied by 2, so 12 plus this one. So we're going to have 13 oxygens in our reactants now and 6 carbons in our reactants. Okay, so what you can usually do is just cross them out. Cross out the old numbers as you're finished with them. And these new numbers are going to be what you're working with. Okay, cool. So our carbons are now balanced. Let's go to the next element. Okay, our hydrogens. We initially had 2 hydrogens, but 12 in our products. Okay, so how are we going to do this? We can put a 6 by our H2O. Okay, now we are going to have, we can cross this out. Now we're going to have 12 hydrogens on both sides. Great success. Okay. But by putting that 6 there, we are also changing the number of oxygens again. Okay. Now we have 6 more oxygens, so we're going to have 18 oxygens. Okay. Now we come down to our carbon is balanced, our hydrogen is balanced. Now we're going to look at our oxygen. So we have 18 in our reactants, but we only have 8 in our products. So what are we going to do? We're going to have to figure out how do we make O2 plus O6 into 18. Okay, so we don't want to put a coefficient by glucose because then it's going to change our carbon and our hydrogen. So luckily in this equation we can just play around with the O2. Okay, and we find that all we need to do is add a 6 by the O2 to get 12 plus 6 here, which would be 18. Okay, and that's how you balance an equation. Now this does take practice, and I suggest going online, finding balancing equations. You can ask ChatGPT for some examples of balancing equations, starting from easier to get your confidence up, okay, and just getting a bit more challenging as you go. If you follow these steps, it'll be a breeze. Okay. You can also start out with the smaller coefficients. Okay, give yourself time, go through them. Start by just doing 2, trying to work it out. Okay, that didn't work. Then go to 3, 4, 5. You see, you probably won't even go up to 6 most of the time. You'll probably just go around 2 and 3 and then find you'll balance it. But just make sure you update all of the elements that are affected by adding a coefficient to a molecule. That is the only reason people struggle when it comes to balancing equations, because they think, I now have 12 hydrogens, cool, and they move on without thinking, oh wait, it affects how many oxygens I have as well. Okay, so always update your elements that are affected by the coefficients, and you'll be fine. Okay, so when it comes to the type of chemicals that we were talking about in the previous slide, you can get compounds, okay, which is something like H2O. Compounds are going to be chemically bonded elements, okay, that they create a new chemical out of those existing elements, okay, so it's not like it creates a new chemical or a new element, it's just elements that are in a different form, okay, that we call a compound. They're chemically bonded, they can only be split via chemical processes such as combustion or electrolysis. Okay. Then we get mixtures. Now mixtures are when different chemicals or different elements, okay, are going to be in the same area as one another. Okay, so they are not chemically bonded, which means they can be separated by physical means. Okay, so you get 2 types of mixtures. You get heterogeneous. Heterogeneous is when they are in different forms, such as your cereal. Okay, the cereal is solid. Your liquid, milk, okay, they can be separated by means of filtration. Okay, a lot of the times when you have chemical reactions and the product is going to be a solid in an aqueous solution, okay, that solid is then, it's usually going to be a homogeneous or a heterogeneous mixture. Okay, homogeneous is when you might have 2 chemicals that are both in an aqueous form. Okay, so they are both liquids mixed together. It could also be 2 solids that are mixed together, okay, such as your ores, like iron ore, which is a mixture, okay, or steel for that matter, okay. So when it comes to these homogeneous mixtures, they can be a bit more difficult to separate. If I take rubbing alcohol, okay, and I mix it with water, there's no way we're going to filter that out. So we have to use other methods such as distillation. We can also use something called fractional distillation. Okay, but distillation is basically separating these homogeneous mixtures, the liquids, depending on their various boiling points. Okay, so you're going to heat it up, and when that alcohol hits its boiling point, it evaporates. We can then capture it, okay, in the condensing tube, which I think we have a picture of here later, and then we're going to have ethanol separated from the water, okay, and you would cut off the heat before the water starts to boil, okay, thus separating it. Fractional distillation, we're going to use a fractioning column, and this separates liquids based on similar boiling points, but it's going to also separate them at similar boiling points. Okay, those beads are going to lead to a condensation of these liquids when they're not quite at the right boiling point, while the other liquid might go through because its boiling point is a lot less. Okay, we'll do some examples of those eventually. Yeah, okay. And then we're going to get to chromatography later as well. Okay, this is the separation using chromatography paper and a solvent. Okay, so here's just a breakdown of this separating mixtures and the different ways of doing it. First we have filtration, which we're going to use filter paper usually for, okay, and a funnel. Easy enough. It's kind of like your coffee grounds. We do the same thing. Okay. Then we have crystallization. Now crystallization is when we have a solution of a solute inside of a solvent. Okay, we're going to heat the solvent up. In this case it's like salt water. Okay, we're going to heat the solution up, and then once it reaches its boiling point, okay, and the first, well, not the boiling point, but just once the first crystals start to form, it's a bit of a chemical process, but once these crystals start to form, we take it out of the heat bath and we let it evaporate. And what's going to happen is those initial crystals that form are going to provide a base that allows the salt to carry on building as the water levels decrease and evaporate, you see. So it's a natural process for salt to also want to attract other salt molecules to it. You see that. If you heat it up too much, if you just take salt water and you boil it off, okay, you don't get salt crystals. You just get powdered salt at the bottom. Okay, it had no time to form these elaborate crystals. So it's something you can try at home, which is really cool, is crystallization. Okay, and then we have simple distillation. So this is, as I explained earlier, separating based on the boiling point, but without a fractional column, okay, without those glass beads, but it's still going to condense, okay, in the condensation tube once it evaporates, and then it's going to be collected, okay. But with the fractional distillation, we use this fractioning column over here, and what this is going to do is separate multiple liquids according to their boiling points. This is used mainly in crude oil, which we'll get to later. Okay.